Hi, my name is Vahan Davoudian. I'm a physics experimentalist for 30 years, and today we are talking about part 4 of 4 for the general relativity simplified. I have already posted or uploaded on YouTube 11 theories as follows. 1. Free-falling object by Vahan Davoudian. 2. Attraction, gravity by Vahan Davoudian. Earth's electric field, gravity because of attraction, positive and negative charges, the theory of separation of charges, Earth's rotation in Pages University with Dr. Gray, new concept in DC motors by Vahan Davoudian. I have to explain this later because this is invention. Radiometer further analysis by Vahan Davoudian, induction, new concept without using magnets. 10. Kepler's second law compared with the pendulum on Earth. And 11, which is today, general relativity simplified by Vahan Davoudian. Well, in fact, I have to first let you know that I'm not going to start 100 years when they started about the general relativity. I have to go back 500 years and then exactly see what the story was about the general relativity. Who started? What was their contribution to? Everything. So anyway, if you think about general relativity, this is the definition. Condition in which the existence or importance of an entity depends on another. Or in other simple language, it means, you are comparing something. Why do I have to go 500 years? Because he was genius. He was one of the best astronomers in history. His name was Copernicus. And he solved the biggest problem for 2,000 years. And then he switched the Earth with sun. He solved the problem. Because before Copernicus, they were thinking the center of the universe is Earth, and they were absolutely wrong. Even Tycho Brahe was thinking, and the Kepler was following him because Kepler was fantastic astronomer anyway. So, and then he solved the problem, and he had to change Earth with sun, and after that everything was just so easy. People now can comprehend, they can visualize, they can conceptualize that Earth is not in the center, sun is in the center. Well, one time he said something profound. It was so meaningful. He said our perception of universe, our perception of solar system, our perception of surrounding, everywhere, it depends on where we are. And I think he was absolutely right. As a matter of fact, 5 years ago I was in Portland, Oregon. People came from all over the world. That was chaos in Portland. There were no hotels, nothing, because people came over because it just happened that the Portland was in a totality. And then I was a little bit away from totality, and something happened, we couldn't go. But anyway, it was a chaos, and my friend, I had to just ask him to film for me, videotape for me. We were almost like 60 kilometers away, and then we couldn't go. We had company, but we watched that. The temperature dropped a lot, like 11 degrees, and then I was thinking that I am not exactly in totality, that a small band. I was a little bit further, and guess what? I just saw only 96%. But my friend was in totality. He was like away from me like 60 kilometers, and he saw the entire thing. So what Mr. Copernicus says is absolutely true. It depends on where you are. Well, unfortunately, we have to go back in history. Galileo was one of the best in relativity because his relativity is so simple. One object is standing still and the other object is moving, or the observer is moving. So what Galileo said, it was so good. Even now we use the same thing. He said you have to have frame of reference. If you don't have a frame of reference, you won't be able to see if you're moving or standing still. If I'm in a car and there is no windows, everything is covered, I have no idea if my car is moving or my background. I cannot tell. So anyway, I have to start today. First of all, we just wanted to thank YouTube because like 2 months I uploaded these videos, almost like 3,000 people watched. That is just incredible. And I just wanted to thank YouTube, because YouTube provided this fantastic service. They are so good, and then we always, appreciate that. And I call YouTube synapse. Synapse is in a human brain, and is connecting billions of neurons. And that's exactly what YouTube does, is connecting everyone. So I put, I upload my theories on YouTube. They do, and some of them are scientists, some of them are enthusiasts of physics. They learn, some of them are students. But what YouTube does is so good, and I think the key is he's trying to help people. And in my opinion, he is promoting, the YouTube is promoting the highest. And God knows, I have no idea how to thank them, because they did a good job so far anyway. I did mention in my previous theories that, entire concept of gravity is not a space-time. Well, of course, please, I apologize. I don't want to, disagree with Albert Einstein. He is one of the greatest. But everybody is, entitled for his or her opinion. So, but I will explain exactly what I mean by that. And then for the Earth, I do honor the existing theory, dynamo theory, but I came up with an entirely different idea. And I discussed it with some professors, geophysicists. They love this idea. But unfortunately, I didn't see any cooperation whatsoever. I proved that in my science lab in 2020, in 20 years ago, that, Earth has an electric field. And I had no idea how to prove it. Finally, after a few years, I found out if I have a disk, and the disk has maybe 100,000 coils on it, and then I rotate that disk so fast, the electric field coming from the Earth will cut through it, and then I get induction. And my guess was right. I demonstrated. Well, of course, I have it in my theories. If you watch, it's called the Earth's electric field. And I had to buy very expensive transducers. And what they do, they detect electromagnetic induction. And I said, Faraday is the key. He helped me to find the Earth's electric field. Anyway, I used to work in Golden, Colorado. I was huge, beautiful city, historic. And then one day I decided with this Earth's electric field, I had to get my compass and go in a railroad. That was like 3 miles, and there was nobody there. It was abandoned. And that was the best day of my life. And, they said, I saw the railroad is like SN. I must have gone like 2-3 miles, it was exactly the same. I said, wait a minute. It looks like something is polarizing everything on Earth. And guess what? They have never been polarized. They have never been magnetized. So in order to prove my idea, I had to get a huge rod. But I have to tell you, it was ferromagnetic. It was never magnetized. And then if you feel it, well, of course, I have a gas meter. Let me still where that gas meter is, I'll show you. About this 20 years ago, and this is the only way I could do my theories, because if you don't have a gas meter as a scientist or physicist, you won't be able to guess, okay, this is S, this is N. Everyone knows that. But how much does it, what is the magnetic field? So this goes to 99,000. It's amazing. It just does with great precision. And then there's a probe here. I can do magnetic field. I can do SN, everything. Even it shows the polarity. And this was a small experiment. Everyone knows that. And London, Fritz London was an amazing scientist. He proved that, whenever you have a not like copper or anything. You know, you have like plastic, Teflon. There's a penetration of electrons 50 microns inside or on the surface. And imagine you rub a balloon on your hair, and earth, the wall is 100% not conductor. But why it stays there? So it is transferring electrons and then making room, it just repel the electrons and then make room, and finally there's a room for the attraction. So my whole idea for the gravity was, it's an imbalance of charges. So the charges are everywhere in universe. But I have to prove it with some other things I'll show you in a minute. The charges are everywhere. It depends on how you do that. This one is for inertia. I used to work in an international place, and then it was in Denver. And then I said, why don't I do this with my friends? So I had a Toyota Camry 1996. I had to take it to mechanic. They took all the seats except for the driver. So I just wanted to see how good laws of inertia is. So why I suspended this was exactly 120 centimeter, and this was 150 grams, and the other one was 10. And then I asked my friend to accelerate. So this 150 gram was accelerating a little bit less, this was accelerating more. Even though they were not pushing on my car, but they were suspended, and at the same time it was rotating clockwise, counterclockwise. Counterclockwise. I said, well, I have to do something else. It was year 2000. I had to get so many, steel balls in airplane. And then I asked the stewardess, I'm going to do this experiment. I said, don't worry about that as long as you're not in a way. So the airplane was taken off almost like 400 kilometers. It was amazing. I saw that, thing was rotating in my hand, that steel ball, it was accelerating forward because of inertia. But guess what? The rotation did not do anything. By the time we get to high altitude, it was exactly the way I want to ignore it. On a landing was the same way. It did not change anything. So I asked my friend to do that. And then he accelerates, this ball goes backward. He decelerates or slow down, that goes the other way. He was going left and right, it was going the other way. I said, well, see, laws of physics works everywhere. It doesn't matter where we are. So I used to go to work in Denver early, like 6 o'clock in the morning, and there was a huge train. It was overpass, and it just happened that every morning, almost at the same time, I could see this train was passing by, and it was almost like 3 miles. And then one day I saw something. I said, wow, thank you, Mr. Albert Einstein. This is relativity. And this was called McIntyre, and as you can see this street, I was going under the bridge, and then the train was over the bridge. And then I saw something weird, I saw something strange. This part was moving, but this part was not moving. I said, wait. That is general relativity. The reason why, one student, young student, asked Albert Einstein, well, why we don't feel the rotation of the earth? And then the answer was so simple that the student loved Albert. He said, what is it? He said, because we're traveling with the earth. And then I did say in my focus pendulum, see, we are traveling with the earth, focus pendulum, but the pendulum is not traveling with the earth. At the same time, it's going back and forth, which focus was the biggest anyway. It was 16 seconds. 16 seconds is a lot. Earth is rotating underneath. So in other words, the plane is changing. This was a good experiment, and then when I adjust my speed 60 miles, and then I realized this is train going always to 60. And then guess what? Here, train was not moving, here was moving. I said, you know what, Vahan, the chances are you did general relativity and Henrik Lorentz transformation. But I wasn't sure about the Henrik Lorentz, but this was an amazing idea anyway. Leyden jar was one of the greatest inventions of the humans before Volta comes and then the other guys come in. But I remember this electroscope is something amazing. My idea is if something works in an atomic and subatomic level, can work also in planetary level. So in Holland, this was one of the best things. Everybody was talking about Leyden jar, and it doesn't matter what charges you bring in, this is adjusting. Negative or positive is adjusting. And then we can see Earth in a bigger scale does the same thing. So I had to compare the Earth as fantastic absorbing both charges, negative and positive. And also noticed something strange. And then I asked someone, physicist, they had no idea. I said, why the bolt of lightning is always zigzag? He could not tell. I said, because it's not ionizing, because of the air density, and he loved my idea. He said, yeah, that's exactly, you never see the, I think it goes straight down. But what happened if you watch, by the time it gets to the Earth, almost it stops right there. And it doesn't matter, 500,000 volts, 1 million, 2 million volts, Earth will do it. So I said, this is the best analogy, so both positive and negative can be attracted. Unfortunately, they were having problem with the 1850s, the telegraph, and there was one German engineer who solved the problem. And my idea was here to show that the Earth is the best conductor ever, best conductor. But I have to talk about Nikola Tesla later, that he was talking about air. Air is not conductor. It doesn't matter how much you have, coil or transformer, it's not going to help. But Earth is the best conductor. And see, this is one copper. Let me show you. There was a copper. I stick it on a soil, and this one was zinc. Well, of course, long time ago, Mr. Pauli was not even there. They had no idea what is the electronegativity of copper, what is the electronegativity of zinc, because it's, flying the electrons from here. That is the key. It's causing difference of potential. And guess what? When I did this on Earth, and then I realized this part is electrons, because I was using my meters like this. But this part was hydrogen ions. Despite the public perception, they say electrons, movement of electrons. No, also the ions also does the same thing. In lead acid battery is the same thing. So one thing I was so surprised, I get exactly 1 volt. But guess what? That 1 volt is not going to light up anything, because you have to go back to ampere. 1 ampere is quintillion. I'm talking about 18 zeros past the point for 1 amp. And then I did something amazing, which I loved it, and then no one has ever done it before. These are the coils for the transformers from the microwave oven, and I had to spend a lot of time, measure this with great precision. Each one is exactly 5 kilometers. I said, what if I connect this back to back and put it in between these and my voltmeter, and you know what happened? The voltage drop was only 10%. I was amazed. So how could Earth be best conductor? Well, in fact, when they're having problem with this, 1850s, his name was the Steinhold, German man, physicist. He said, why do you use second wire to bring back the telegraph? And they said, why? He said, you can use only one wire and the return can be Earth. And God knows he solved the problem. Not only money-wise, imagine how much they had to put wires and wires. But the Earth is the best conductor. So that's the way he did it anyway. And this is my imagination, of course, they love this idea. Because, when you jump up, almost like 1/3 of a second you are in air if you're a good player, then you go down. And then you can jump if you're a good player, basketball player, you can jump 1.20 meters. But imagine, one of these basketball players is 80 kilograms and the other one is 100 kilograms. See what happened. By the time they jump up, if they have a scale underneath, it's not going to show any acceleration. But if this man, which is 80 kilograms push, this man is going to go less, they drift apart in inverse proportion to their masses. But if the 100 kilogram pushes on 80, he is going to be accelerated more. I said, you know what? Sometimes it doesn't make sense. Maybe I have to get this in a space station. Same thing happened. If I'm in a space station, exactly the same thing. But the only thing, we have to join hands and imagine John and Julie. Julie is going to be accelerated more because Julie is 80 kilograms, but John is 100 kilograms. So imagine in space, you cannot go ahead and check your acceleration, how much you weigh, because they have to change your acceleration. So this was my idea, and then I discussed it with so many physicists. They love this. They said the only way you can find out that you have your mass or you have weight, you have to change the acceleration. Free fall is not going to show because you're not doing action and reaction. So these two, John and Jill, they are on the floor, but it doesn't matter. Laws of physics works everywhere. They push each other. They are drifting apart, inversely proportional to their masses. Albert Einstein, they never did this experiment. And imagine if you have a spacecraft like this, they have two holes, and then the light goes through, it's going to go straight. But if this is accelerating, it's going to bend. Because I don't remember having seen this, done in anywhere. So they didn't do this experiment. It's just a thought experiment anyway. But this is my favorite, and he is physicist and chemist. His name is Don Petit. And then when I saw this many years ago, I was going nuts. I said, hey, my idea is right. Gravity is not playing any role. So they were having problems, when there's a supernova, it just explodes after billions of years. In space, we got trillions or quintillions of parts, chunks of, everything. And then they had no idea how do they clump together. So Mr. Don did this, Don Petit. He had coffee, he had sugar, he had salt, but the salt was the important one because he put it in a plastic bag, and while he was free falling, he realized that salt is clumping together. And guess what? There's no gravity there. The only determining factor is electrostatic energy, electrostatic charges. And he was right. then the mystery was solved. Because this was so important. This was so important in the International Space Station. It solved the problem for astronomers. Now they know, whenever we have so much debris in space, like even nebula, they get together, and finally they become a star. But they also said something good. They said if this clump together with the electrostatic charges, if it's like half a mile, it's enough to grab more things. It's like a vacuum cleaner, it just grabs more and more. Because I think each planet might take like billions of years. And we want to thank Mr. Don Petit that he solved the big history. And when I'm thinking in space, the gravity is not playing any role, even though there is a gravity, but it's not playing any role. Sometimes they say, well, moon is geologically dead. Well, of course, Mars is geologically dead. But why moon has a gravity? There is no iron. If you compare with Earth, dynamo effect, moon has electrostatic charges only. And it's pulling us so good, and it's adjusting us, and we're so lucky we have the moon. Mars is the same way. It doesn't have core, but Earth has a core, but it doesn't matter. I mean, my idea is if I take a dynamo to Jupiter, Mars, it's not going to attract any apple or orange or other things. It's going to attract only what? Ferromagnetics. I mean, even if that is true, it is not going to attract everything. But what we're attracting on the Earth is because of charges. When I pick up something from the Earth, I am, disturbing the charge. The charges toward this, let me show you. This is on the ground. The charges underneath is more. So when I pick this up, I'm giving more energy. It has to go back where it is. And then, like I said, I discussed the differential forces. It knocks us down. But unfortunately, Albert Einstein worked 30 years, the theory of everything. They could not do anything for the gravity because it's attraction only anyway. This is the one I just discussed a few minutes ago. And like I said, it doesn't matter where you are, always more mass is playing a big role. If I take 1 kilogram outside the Kuiper belt and then I push it, I need more force to accelerate. And there's no gravity there. But you know what? The mass is not changing. The acceleration, local acceleration due to gravity is changing. And this is Albert Einstein, famous innovator. And it is so good the way it is. He explained, that was fabulous. And then your innovator here, and then you have no idea of gravitational field, or if here you're suspended, like, and then when they fire the engine, but you don't have frame of reference to see outside what you can see. I don't know. Am I falling toward the Earth or they fire the engine? You cannot say. And that is simple. Just you have to have frame of reference. And this is my gravity. I came up with this. And imagine there are 2 airplanes. They're flying same altitude, exactly same altitude and same speed. But they have a little, a small hole here, small hole here. And then they watch each other, and then they have no idea who's moving, who is not moving, or because, like I said, they have the same speed. So I came up with this: A and B are standing still, not moving. A and B is moving simultaneously, so we can see Galileo's relativity. And then, imagine, you cannot tell. Always you need a frame of reference. And this is for the static of charges, static charges. See, one of the greatest ideas for the charges, because I do have one, I worked on it like 4 or 5 years, it's called The Theory of the Separation of Charges. You can see on YouTube, that is almost like 1 hour, because I cannot explain everything here. The idea for the attraction is induction. If you don't exchange electrons, you won't be able to attract. So why do they say dynamo effect is attracting people? No, it might be able, to attract ferromagnetic, but I'm not ferromagnetic. Apple orange is not ferromagnetic. Plastic is not ferromagnetic. So imagine all these things happen when you are disturbing the charges. And imagine we see thunderstorm, we see lightning, with lightning, we have no idea how do they get together that fast, and then they have to discharge it. So, this one is done with the greatest mind in history, Sir Isaac Newton. I remember I used to have so many lectures. Always I try to simplify things. I said the most important for the laws of physics is like a balance scale. If you have a scale, you can go to micrograms, nanograms. Well, of course, we can do micrograms. It doesn't matter. If you change the left side, it's going to go to the right side. And laws of physics is always like that. Force is mass times acceleration. If you don't have mass times acceleration, you don't have force. And Sir Isaac Newton did something amazing. And this experiment by far is one of the best, and it changed our understanding. And imagine, you just analyze the light here, and then see, you got all the rainbow here. See how genius he was. He put another prism upside down, he culminated those, and then again here. So what laws of physics tell you, they are universal. You can go to the left side, you can go to the right side, they're exactly the same. And this is my favorite, Galileo. And imagine, this is a simple, very simple, let me get my ruler. This is a simple experiment. What it is, Sailor is here and he's dropping a ball. So this guy over here, Sailor, he sees that, that ball, 100 gram or whatever, the steel ball is falling straight down. You see, that line is perpendicular. But Sailor does the same thing, but this time, this man is the observer. Observer is not moving with the ship. So observer is standing still, but the ship is moving. So they can see that is curving. That's exactly what Galileo proved, that you have to have frame of reference. Let me see, what else do I have here? And this is for Nikola Tesla. Well, of course, that has nothing to do to gravity, but I just wanted to emphasize, because he was one of the greatest minds in the history of science. So, okay. I hope I can see everything. I can show you guys everything. Let me see if I can see this. Yeah, I think I can see. Maybe I have to adjust this a little bit more. Okay, that's better now. So Nikola Tesla, by far, was one of the greatest scientists in history. So imagine, this is Van Allen belt, and this was my imagination. So I put his coil over here, and that car is called Michael Faraday's cage, because it's conductor. If lightning happens, you go inside, you're not going to get hurt, and you see that's the thing. And then one important thing happened here, which I'm always upset. and Luigi Galvani stole his ideas, 15 of them, and then he got the Nobel Prize, and I was so sad. That is the only plagiarism in a science that, nobody will forgive that. And they were both engraved, so they got the Nobel Prize from Luigi Galvani to Mr. Nikola Tesla, which was not good anyway. So this is the Earth, but you can see how lucky we are. How lucky we are. It's the ionosphere. See, this is the Earth. So it's exactly, I compared with the cathode ray tube. In cathode ray tube, if you have a beam of electrons, you can deflect. This is exactly what it is. You're sending radio wave, it's coming here, bouncing up, all the way. It's going to China or it's going to Japan. And imagine what Nikola Tesla did. It was a little bit exaggeration because by far he was disagreeing with his professor because his professor, I don't know the name, one time he was walking in Budapest with a friend, and then he stopped, exactly like Einstein said, was the best moment of my life. He said, in order to get AC power, they have to change the magnetic field. And then he was right. He came and spoke with the professor. Professor didn't like it, but he proved that if you don't change the magnetic field, you won't be able to do anything, induction. And now we know it is true. Without the AC, we could not survive, alternating current. With DC, we cannot. And then I don't know why Thomas Edison was doing that much, propaganda and then a smear campaign for him, but that was not good. So one of the biggest mistakes of the Mr. Tesla was that, he just wanted to send 1.5 miles in air. Air is not conductor. And he was genius. How could he not know that, the Earth is not conductor? He was sending 1.5 kilometers, and then they could light up, something like, fluorescent or something like that. That was incredible. But there is no way we can ionize the Earth. Well, of course, there's some charged particles scattered everywhere. But the reason why we ionize everything, because it's a cascade. We have to ionize this molecule, that molecule. And I think Mr. Tesla was wrong. The Earth, there is no way you can do it from Earth. But I have a hunch you could have done it by Earth. But that's another problem. One time in El Paso County in Colorado, and then he did it by Earth, and then the poor horses were jumping up and down. So that's not going to work. So overall, it's not going to work because Mr. Tesla should have known about the 1859 when there was a storm, because every 11 years we have the storm, mass corona ejection, and then the people saw in Boston, they did not turn on the machines, the telegraph machine, they were working. They had no idea. So what happened? He was right if we could bring the ionosphere down to the Earth. See, there are charged particles here, but that's the problem. Ionosphere is not going to help us because we cannot do any conduction or anything because it's too much charges. There is no way. So that was his big mistake. And I think Nikola Tesla was overall, he always, remember, he was eccentric, and then he could not defend himself. And then the sad part was he, died destitute and penniless and so poor. And I think why people did not help him, I don't know. But he changed everything in the United States in 1930 when the World Fair. Tesla was one of the greatest icons, but unfortunately his life was miserable, and that's the way he lived. But I don't know, I don't like it anyway. This is what I have here. There's some cases of plagiarism. You know what? I don't like this word. Something happened in history which, Mr. Hans Christian Ørsted was genius, from Holland. And then, that was not his idea, some student did. And then the compass was on, he went to teach in a class, came back and they said, well, when I turn on this light, the compass was going back and forth crazy. And then he discovered there is a connection between electricity and magnetism. Well, of course, that was amazing. That was electricity and magnetism. At the same time in Italy, something happened so amazing. Mr. Luigi Galvani, he was a doctor or an anatomist, and then he had no idea about the physics. And then they were dissecting a frog, and then frog was dead. When they put two different metals, that frog twitched. They said, well, he's dead. This frog is dead. How could they do it? And then immediately, Alessandro Volta found out what the problem was. So, of course, they become a big enemy. They say, you're plagiarizing, so and so. But I think, to be honest with you, 50-50. 50 goes to Luigi Galvani and 50 to Mr. Volta. Because he said the reason why you got this voltage because of different metals. You got copper, and then you got iron, you got aluminum, you got zinc, and he was right. But unfortunately, he was insisting, Luigi Galvani, this is animal electricity. No, there's no. If I have a water or tea, I can put two probes, it's going to show half a volt. Then what this means, there is no animal electricity anyway. Then there was another case, Tycho Brahe was an amazing person. He was a good astronomer, but he didn't have college education. And then what was his name? Kepler was there. It was not plagiarism. What they did, he got all this observation, because at that time telescope was not even invented. All those observations, and then he developed, and then we owe it to Mr. Kepler that Kepler did something amazing with those three laws of planetary motions. It changed the world. In fact, 2 weeks ago, I had a theory called Kepler's second law compared to the pendulum, and I proved that everything is the same. In the smaller scale, we have pendulum, equal areas, equal times. So is in Kepler's law. And then when Kepler did those, we had no idea why the space station is going 90 minutes. And I told myself, yeah, this is the second law of Mr. Kepler, because it's closed. Why Neptune takes 164 years? Why Mars takes like 2 years? Why Earth go 1 year? That's the reason why. So the Kepler could see like 400 years ahead. And then if you compare, we have like geostationary 22,000, I think. Then we have like, I think 32,000 kilometers. And imagine the further you go from the Earth, and then the more, you go slower.